Welcome back, everyone, and sorry to the people watching asynchronously who don't have power due to the storm. This was the best solution that I could come up with. Having rescheduling for a different time and then especially so close to the end of the term would have been difficult, especially given that there's another very long lecture scheduled for tomorrow, right? First off, does anyone have any questions?
Somehow I cannot log on to normal set right now. I'm just wondering
Oh,
if anyone has the same issue.
I can check during the break whether or not Marmoset has issues. I hope that the department doesn't have a power outage. If Stony Brook has a power outage, then Marmoset is being hosted on the Stony Brook math servers. Is it down?
Yeah, I tried for many times and it says this site cannot be reached.
Oh, I see. Okay, I will definitely ask the sysadmin.
Okay, thank you.
Yeah, I've seen issue with that.
Okay, if multiple people are having it, then it's definitely a problem with the Stony Brook mathematics servers, possibly related to the power outage. I should have played Neighborhood to Power Out by Arcade Fire at the beginning of today's class. That would have been the obvious music choice. Sad, I missed that. Okay, so I'd like to begin with something that I discovered last night. And it's that most generally, you don't screw with substitution. Substitution screws with you. Our definition of substitution was wrong. There was a question last time, how do we know if it's right? And the answer was, well, it's a definition, so you can never know. You can try and sleep at night thinking that you have a right definition of substitution, but do you ever really know? Can you ever really know? And the answer is probably no, because look, this is actually, so substitution was also related to this notion of alpha equivalence. And one way to put it is I wrote down the following two statements. So this is how I came to that realization. Suppose we have for all nats n, for all nats m, the statement that plus nm equals plus nm. Then we can consider variations of the statement. We can consider the following two statements. One, for all nats n, for all nats n, and the second one being for all nats m, for all nats m. And then I have the statement plus here n equals plus nn. And here plus mm equals plus mm. So if you look at the logical meaning of these three statements, well, the logical meaning of the last two is technically the same, although, yes, but they're not the same as the meaning of the initial statement. So first off, why does the first statement in blue not mean the same thing as the red statement? So I guess as a first question, what did I do to transform the red statement into the first blue statement? Anyone?
Did you substitute n for n for the second for all?
Yes. So I took the second for all quantifier. It previously used to be an m, but I replaced it with an n, right? So I performed this renaming. Now, this renaming changed the logical meaning of the statement. Why was this renaming not allowed?
You already have n appearing in the sentence.
Right, but not just a matter of appearing. If we look at what this sentence is, it's for all knots m, right? And then you have the body of the expression. And the body of the expression is plus, well, in this expression, sorry, let's look at the original expression. If we just look at this expression, that's a logical statement. And what can you say about n in that logical statement, in the statement that's underlined in green?
Oh, n is not binding.
It's more precisely in the language of last time, it occurs how?
Oh, occur freely.
Yes, so n occurs freely in this statement. And so we are not allowed to perform this renaming because we are not allowed to rename the second quantifier, because if you look at the expression which that quantifier defines, including the quantifier, n appears freely. So renaming m to n is not allowed, since n appears freely. Occurs, rather. In the expression, in the green expression. Right. But what about the second example? How did I get from the first red statement to the second blue statement?
You substituted the first quantifier n with m.
Right. So I changed m to n. Now, that also isn't allowed. Well, when I say it's not allowed, I mean that the statement changes its logical meaning. In both of these blue statements, if you look at the m or the n inside the plus expression, both refer to what is bound by the innermost quantifier. So the outermost quantifier, that variable of quantification doesn't appear anywhere in the inner expression. Okay, now why was the second renaming not allowed? So first off, if we look at this expression, let me highlight it like this. If we look at the if we look at the first quantifier, we're now discussing changing the name of the first quantifier. It's associated to this entire expression, right? Does m occur freely in that expression?
Yes.
Why?
Because wait, n occurs freely. Because it's not binded. I don't know how to explain it.
Well, there's an occurrence of m here, right?
Yes.
But that occurrence of m is bound to this quantifier. It's not a free occurrence of m.
No, it's not.
So m does not occur then. M does not occur freely in this expression.
Okay.
And yet, nonetheless, this substitution is illegal because it somehow changes the meaning of the expression, right? Why does it change the meaning of the expression? What exactly happens? I'll write causes. What's the problem then? Sorry, renaming n to m.
Causes variable capture.
Yes. Why?
That should be the counterexample of our previous definition, right?
Right. So in our previous definition, we just checked, we said we could rename so long as the new variable wasn't free in the expression. Well, here, m is free and is not free in the expression. So in our previous definition, we would be allowed to rename n to m. Whereas here we see that that breaks the example. So, but why does it break the example?
Because n occurs freely?
Well, I mean, we're looking right now at, we're trying to say something about the statement that's in blue, right? The statement that's underlined in blue above, the entire statement. Neither m nor n occur freely in that statement.
Okay.
Now, so we make the renaming, and the problem is that after we've renamed it, we changed n to m, right? So this is where the n used to be, right? And so we want that to refer to that m, but the problem is it doesn't, because now it refers to this m, right? So what was the problem with m?
N does not occur freely.
Well, that's a true statement, but that's not a problem. Sorry, we were looking at the original statement, and we're trying to consider the idea of whether or not we're allowed to rename n to m, right? So neither m nor n appear freely in the entire expression, occur freely. But what can you say about m in that expression? So the actual technical term for what I'm trying to say isn't a term that I've told you yet. I'm about to define it, but I want you to tell me just at a high level, what's the problem?
Is the second quantifier?
Right. So there's what is called a binding occurrence of m. In other words, it's occurs in a quantifier because there is a binding occurrence of, so this is a new term, of m in the body of the expression. So when we defined what free variables were, we didn't actually, the only thing that we cared about in binders, in variables of quantification, were that's free in stopped and returned false if we reached a variable of a quantification which matched up. Well, we need to write another function, which is bound in the expression. So we also need to check that the variable to which we're renaming does not have a binding occurrence in the body of the expression. So in other words, what we need to do to fix our definition of substitution is that we need to define, we're looking at the case of substituting inside of a lambda. So let's say we have lambda x dot t, and we want to make the substitution y goes to s. And now we are assuming that we need to substitute. So when is the case that we need to rename? When would we need to rename x? Why can't we just substitute in the body of t?
When x occur freely in S.
Yes, if x occurs freely in S, then the definition was that we needed to rename this. We needed to change this into lambda z, and then we took t, and then we replaced all occurrences of x with what?
Z.
Yes. And then after doing that, we took this term and did what with it?
Y substituted to
Yes, exactly.
S.
Now, so that's the same as our definition as it occurred before, but before we said where this variable z, where z, before we said does not occur. What was our condition?
Z does not occur freely in S or T.
Yes, exactly. And now what we need to do is we need to add another condition, or, and also. Now the problem is that, so what can the problem be then? We see that the problem is that if we replace x with z, there might be some quantifier which has z as its quantifier, and then the meaning of x would no longer be bound to the outermost lambda. So this is a condition that we're doing in checking in renaming the variable, right? So what do we need to check? Using the term of binding occurrence. And also z. So if z is the the formal parameter of some lambda, then we say that x has a binding occurrence.
Z has no binding occurrence in
Yes.
X.
In what?
Not X, but T, I think.
Yes, maybe? Z, and also Z has no binding occurrences in T. So this definition of substitution, as far as I believe, and I've checked, so the Balker's notes also need to be updated. We were both surprised to discover this. And we looked in another book, and looking at the references, people think that this definition is correct, but can you ever know? Can you really ever know? That's a disturbing question. I don't think you can ever really know. But no, this is probably correct. So we need to also add this final condition. What is the lesson of all of this? You don't screw with substitution. Substitution screws with you. You are going to implement substitution incorrectly no matter what you do the first several times. So substitution is even scarier than it was before. So that's just a correction that I wanted to issue. The main thing that you have to know about substitution is you should rewatch what I said about substitution, and you should realize that it's scary. But also you should realize that these variable capture issues come up, and they come up in real mathematics. Even so, with questions like how to rename statements, variables of quantification. Here's an example where both issues can come up when in renaming. But I mean, all of the exams are open book, and it's not as though you have to memorize this for several reasons. But understand that substitution, it has a lot of subtlety to it, and everyone needs to see this once in their lives. Any questions? Oh, by the way, do people hear a lawnmower outside of my window? I'm assuming the answer is no, right?
No.
Okay. Zoom is really good about filtering out background noise, even when it appears pretty loud to me. Right, so let's get back to where we were before. And I want to also restate what happened. So we showed several examples in which it would be desirable to mix terms and types in expressions. The prototype of expressions that we're going to are statements of the form, for example, for all natural numbers n, that n equals n. These are the types of logical statements that we'd like to make. So this is like a logic wish list. And what happens here is that this is a type. This is a proposition. It's the proposition that every single natural number equals itself, right? But inside of that proposition, you have variables occurring, and the meaning of the variables is really like a term. In fact, you could even form the type, let's say z equals z. And there you have a type with terms occurring in it. And so what we had to concede was that, well, terms and types aren't so distinct. And so we put all of them into a single grammar. And I'll write the grammar with just T. It's written with expression in the notes, but I'm writing it by hand. And if I wrote expression every single time, it would be a bit painful. But this includes both terms and types. So as before, we had variables, we had abstractions, and we had applications. But here, T no longer just means a term or a type. It can also be, sorry, it's no longer a term, it can also be a type. One of the types that we had was type. Another of the types that we had was arrow types as before. And a third of type that we had was the more general form of a for all statement. And also, I'll write it here, let's also include annotations, and I'll discuss annotations in a second. So this is a new case. Now, since we've mixed all of these into our grammar of expressions, every single grammar construct, when we're doing type checking or type synthesis, has an associated rule to it. So before, when we had a special grammar for types in propositional logic. And in that grammar, anything that you wrote was a well-formed type, whereas that's no longer the case here, because you're allowed to form ill-formed statements by this grammar, like for all x in lambda y dot y. Let's say x. This is ill-formed because what you're quantifying over shouldn't be in any reasonable way interpreted as a type. And then the question is really, what is a type? Well, types are things for which it makes sense to ask whether they classify terms. The reason that I write may as opposed to do classify terms is that you can write types that correspond to logical statements that are false, in which case they shouldn't have a proof. So some types might not have terms. Types corresponding to false logical statements will not have terms. But whenever we write something on the right-hand side of a colon, it should be something that Proust would reject if it is not a well-formed type. Now, what is a well-formed type? Now that we've thrown all of our type constructs into the grammar of expressions, there are rules associated to each construct that say when a specific instance of that grammar construct is a well-formed type. Any questions? And I can give you all of those rules. This is just for review again. So the first rule, let's cover them not necessarily in a row. The simplest rule is that for this construct of type, that you can synthesize its type as type. So this is one rule. And that is the rule that corresponds to this variant in the grammar of expressions. Now, let's consider the rule for arrows. So if you had, let's say, T arrow W, then this should synthesize, this should define a type, provided what? When does T imply W make sense? Or T to W make sense as a type? So as an example, if I wrote lambda x dot x implies, let's say, nat. This does not make sense because this could be, in programming languages world, interpreted as a function that takes terms of type lambda xx, right? But that doesn't make sense because lambda xx on its own doesn't classify terms. So the reason that that doesn't work is because lambda xx, it does not have type. It's not a type. The left-hand side doesn't classify terms. So what do I need to check to see that an arrow type, an implication type, is indeed a well-formed type?
So you need to check in context gamma. T is a type.
Yes. Type checks a type.
Type checks type, and
And
also in context gamma, W type checks to type.
yes. Now, what actually we have is that all of these implication is actually syntactic sugar, is shorthand for all, and then you write you refuse to give the variable of quantification, you put an underscore. So for all proofs of T, a proof of W. Where now there's nothing that can occur. But more generally, we also have for all types. And in for all types, the variable of quantification can appear in the type. So here, for example, for all n equals n occurs as in, well, there's a binding occurrence in the quantifier, and then there are occurrences inside the body of the universal quantification expression. So implication is just a special case of for alls where the variable of quantification doesn't appear in the body of the right-hand side. And we would not even give it a variable of quantification. We put an underscore, which has a special behavior when we implement it. But in that case, if we have the statement for all, let's say, x in T, W, when is this a well-formed type? What do we need to check?
T must be a type.
Yes. And also?
In the context gamma and x
Good.
of T, W is a type.
Yes. So in order to make sense of W as a type, we have to actually know what type X has in order to make the judgment. So for example, if we're trying to type the statement for all natural numbers n equals n, then it doesn't necessarily make sense to oh, sorry. Then if we're working in the empty context, n equals n does not make sense as a type, because what does n mean? Maybe n is some very meaningful broken expression that you can't put inside of the equality. You need to know something about n. And so that's why we throw things into our context. Since x occurs in W, we can't just forget information that we know about x. We know some information when we're trying to type W, and that's that x has type T. And that information will come up and it will be relevant in the typing. So we do have to keep this. So now we've added 3 really type constructs here into our grammar of expressions, and each one of these now has an associated rule to it. The conclusion of the rule is always that we're able to synthesize type, and these are what the premises are. And in general, whenever we add a new construct, we're going to add a type corresponding to that construct, and we're going to add a rule that says when a grammatical occurrence of that type is well-formed. I'll use the words well-formed. So these are rules that types are well-formed. And then we had our computation rules, not our computation rules, but our typing rules for all of the other constructs. And these are similar to what we had before. So for example, well, we gave them last class. Let's give them again. So first off, variables. If in some context gamma, you're trying to look at a variable x, then let's say what's the rule for variables? Let's say x synthesizes type T in context gamma provided what?
X has type T in context gamma.
Yes, so we do a context lookup, and we see that we know that x has type T from the context. So this is a context lookup, and this was the variable rule as before. Now, what about the rule for typing lambdas? So let's say we have lambda x dot t. And we want to type check this against a for all statement. When do we know that this type checking succeeds?
So in context gamma and little x is a proof of T. That's the context.
Right. So you're going to add x into the context with annotation with type T. It would be very nice to ensure that whenever we add something to the context, that the annotation is indeed a type.
Okay, so first we check whether T is a type.
Yes. And after we've done that, we know that it's kosher to add it to our context. Then what do we do?
Then we do in context gamma, and X has annotation T. W is a type.
Oh, okay. Let me, there's one very important thing that I need to correct. Here I wrote a capital X and a lowercase x, right? I'm going to write the same lowercase x in both occurrences, and I'll explain why in a second. So, okay, let's suppose it's lowercase, then what are we checking?
W is a type, or we can try to check whether T type checks to W.
Yes. And in this case, if W is not a type, it'll get caught elsewhere in the type checking. So in order for the original thing to have been a type anyway, if the thing here is a type, then this check will succeed no matter what. So this version of the rule is sort of valid even if what we're trying to type check isn't against the type. If it succeeds, then we'll know that for sure that it's indeed a type. We are also ensuring that anything we add to the context, for example, is a type. We're going to assume that everything in a context, its subscription is a well-formed type. Now, here's the thing. What happens if we're trying to check against a statement where why is it important that this x is the same as this x? Because if you look at this addition to the context, x might occur in T, right? Because it's lambda xt. Most likely, in fact, x will occur in T. But also, x might occur in W, right? Now, let's suppose that we had two different variables. Let's say we had y, and let's say we also added y to the context. But then the problem is that the variables in the context are meaningful for both the term and the type W. So if we add something to the context, it has to be meaningful in both terms. So in general, what we want to do is we want to apply alpha equivalence in order to make it so that both of these match up. So that when we add it to the context, we know for a fact that we're not going to add meaning to something that's meaningful in T, but not meaningful in W, because that would cause variable capture, unintended variable capture as well. So in general, in order to make this rule work out, you have to make these two agree. Now, if there's an underscore, technically things with an underscore are also alpha equivalents to things without an underscore. So the correct way by which you make these two equal depends on the implementation of alpha equivalence. And that's not a detail that we're going to discuss. But I do want to just highlight that it was important that both of these matched up. And the reason is that when we add x to the context, it provides meaning to occurrences of x in both T and W. And so that was our old version of this rule, was the implication introduction rule, but now it's the for all introduction rule, because implication is just a special case of for alls. Any questions? And then finally, our third rule was about typing applications. So I'm not going to write well, it's a synthesis rule as it was before. But what are the premises? What's the first thing that we have to do?
Check whether T little t is a big T.
There's no little t or big T yet. Right now, you're just asked, given the synthesis problem, right? You're just asked to synthesize the type of an application in context gamma. You only have what's written on the page right now. what did you do before when talking about the implication elimination rule? What's the first thing that we did? For all introduction is supposed to be similar to implication introduction, and for all elimination is supposed to be similar to implication elimination, because implications are a special case of for all, right?
We check whether F can be synthesized to some sort of implication.
Yes, but not an implication of for all statements.
Yeah, in our case, that will be a for all statement.
So we try and synthesize the type, and we try and match the synthesized type against the for all statement. And then if that succeeds, then what? Also, I want to change the name T here to, let's say, A.
So we check whether A has type T.
Yep. And then if both of those succeeds, we're able to synthesize the type, right? But what's the results? What's the resulting type?
That will
So what's
be that will be W with each occurrence of X substituted with T.
Exactly.
Well,
We need to
let's
substitute.
with A.
Yes. With every occurrence of X, well, every occurrence meaning all relevant occurrences of X substituted with A. We need to, in general, substitute to compute the results type, and that's the for all elimination rule. And now, just for the sake of completeness, I also want to tell you what the rule for annotations is. So annotations are supposed to be this thing that lets us switch from synthesis to checking. So in context gamma, suppose we have T:(T), an annotation. Then we're able to synthesize its type as T provided what?
In context gamma, T type checks T.
Yes. Now, for a technical reason, I'm also going to want to check that T is a well-formed type. And I'll explain why this is in a while. And this is the annotation rule. So here is our grammar then. Here is our original grammar. If we look at it, there are 7 variants in the grammar of expressions, and there are 7 rules corresponding to those variants. Technically, a rule might have both a synthesis and a checking version, but we have these. So these are 3 rules for checking whether a type is well formed. And then these are the variable rule, the k which corresponds to variables, the case that corresponds to lambdas is for all introduction, and the case that corresponds to applications is for all elimination, and then annotations. But finally, there's one rule that we're missing, and that's the turn rule, which will take on actually a bit of a different technical meaning. And the turn rule was that if we're trying to type check T against type T, then what are we allowed to do? what's one way that we can type check? What was the turn rule before?
In context gamma, T can be synthesized to a type T.
To type W, let's say, and then what else?
Then W is equivalent to T.
Yes. So that was the turn rule for switching between synthesis and checking. And at the moment, it looks like this rule is just an artifact of the bidirectional approach and that it's not really meaningful in the monodirectional approach. But in the monodirectional approach, we can also state this rule. We can put colons instead of both of the arrows. And it looks like that's a completely useless rule at first, but in predicate logic, it will actually have a use. So 8 grammar constructs now. Then these are the basic rules concerning logic with for alls, which subsumes logic with implications. We started with the implication fragments when we started with propositional logic. Now we're going with the universal quantification fragments, in which the only type formation that you have really is for all statements. But as an auxiliary thing, in order to have something to quantify over, we introduce type into the grammar. So this is our starting point. This is the analog of the implication fragments, these 8 rules. Now, if you look at it then, before...
I have a question.
Yep.
For annotation, T synthesize type or type checks type?
Oh, thank you. I'd like to write type checks to type. That's better. Good. Now, before, for example, let's consider the empty context, and let's consider the propositional, let's consider A implies A, right? Are we able to synthesize this as a type? Can we do this? Let's just look at the rules. These are bidirectional rules. So writing a proof tree should be automatic, right? A computer should be able to do this. Will Proust be able to synthesize this as type? So what happens if we ask Proust to synthesize the type of A implies A in the empty context? Let's look at the rules. So if you have an implication, then what does this rule say? Right here.
We should check whether A is a type.
Yes. And I guess we do this twice. And then you'd apply the turn rule and you try and synthesize it. And then what? A is a variable, right? So what rule applies to variables?
The variable rule.
Right. And what does that cause? So what does the variable rule do?
But we have empty context.
Exactly. We have an empty context. So there's no variable binding to A in the context. So we don't know that A is a type. We don't know this. So this fails, and so this fails. So A implies A is not a type in the empty context, which was very different from propositional logic. Because in propositional logic, we had A implies A. It was a type by default because there was a special grammar for types. If you had anything that you wrote on the right-hand side of the colon, the variables in there automatically meant types, whereas this isn't automatically true. Because here, we don't know whether we have a lambda variable, a variable in the language of lambda calculus, or a propositional variable. We don't know which one of those is the case. So unlike propositional logic, A implies A is not a type in the empty context. Unlike, let's suppose to say in propositional, is not a type in the empty context. And if we thought then about what A implies A was, it's the statement that if you have any A, like it's raining outside, any logical atom, that thing implied itself, right? But I said for any logical atom, right? So how do we fix this? How do we take the statement that anything implies itself and make it be a logical statement in the language of predicate logic? So we want to say that anything implies itself, right? How do I write that as a logical statement in this language?
We have to know that thing is a type.
And how do we know that?
Add that thing to context.
I'd like to write a logical statement that makes sense with no free variables. So, for example, A might be it's raining outside, right? But in propositional logic, A implies A doesn't really just say that it's raining outside, therefore it's raining outside. It says for any proposition, for any logical statement which you can make sense of, that statement implies itself, right? A was a propositional variable. It didn't stand for, so for example, when in Racket, when we had the identity function, we said that the type of the identity function was A implies A, or A to A in Racket. Meaning that we could type ID to not, for example. So if you gave the identity function a natural number, then we'd get a natural number back. But in the identity function, we didn't have the type not anywhere. If you gave it anything of any type, it would give you the thing back, and it would still have the same type of the argument that you gave it. So it's not just saying it's not just some specific A. It's any logical statement implies itself. How do we write that in predicate logic?
I think we have to use the for all in the context. I mean, not in the context, as a syntax, as part of our language.
So we'd write for all A,
Yeah.
Then let's leave this blank. A implies A. So for all logical statements, that statement implies itself, right? Now, here's the question. What do we quantify A over?
A has to be a type.
Yes. So in predicate logic, instead of saying just A implies A, we'd say for all types A implies A. Now, all logical statements can be reinterpreted as being types. So we take all of the propositional variables that occurred in the propositional statements, and we put quantifiers outside of the statement saying that they are types. And so this statement now says that for all types A implies A, and a type might be a logical statement. Now, how do we write a term for that? What is a proof term for that? How do we prove this?
So we start with lambda.
Yes. And then what should I call this variable of quantification?
Little a.
Little a. You said little a. Okay, and then what?
So A.
Okay, well, let's see if this works. Because remember, when we want to check if something works, a computer can do that for us, right?
I mean type.
What do you mean type?
Lambda A and dot type.
But okay, so this is a function that takes anything and returns type. You mean this?
Yes.
Okay, well, I mean, the computational meaning of that is that's a function. You give it anything and then it returns the expression type. Okay, well, fine. Let's see if that proof works. So we start off with the empty context, then we start off with lambda A dot type, right? And you're claiming that this will type check for all A in type. Let's make the variables coincide, right? So let's make it for all A in type. A implies A. Then what happens? What rule do we apply?
For all introduction.
Right, and so what do we get? What do we need to check? Let's see. In the for all introduction rule, we need to check that the thing that we're quantifying over is a type. And we also need to check, we throw a thing into the context and then type check the body, right? So let's see. Is type a type? Yes, it is. Formally, this follows from the turn rule. So we're done with that branch. Now, what about the second premises? Well, what do we do here?
In context, empty. In context. X.
Well, A.
Oh, A has type.
That's what?
Type checks A to A.
Yes. And that's a problem. That's not going to happen. The only thing that type checks to is type. So that's an issue. But this was a good thing to go through because we see why it's wrong, and that suggests why we would get something that's right. So that doesn't work. But it's the same thing that we had before. These rules define a program, and then Racket just follows that. Proust just follows this program. So it's purely mechanical how you type check once all of the rules are given. So that term doesn't work. So what term would work?
Oh, I think it should be lambda capital A.
Yes. And then?
Another lambda, I think.
Yes. Let's call the second variable what?
I don't know, B?
Let's call it little a.
Okay.
What?
Then our goal should be A. So,
Capital
and
A.
little a.
So, okay, that's the term, and this is something of type capital A, right?
Yes.
So this indeed, well, I'll write it on the next line. This indeed has the type for all A in type. A implies A, or A to A. And this is called the polymorphic identity function. So the idea is that for every single type, we get an identity function. So for example, if you take the polymorphic identity function and you apply it to the type natural numbers, then you get the identity function on natural numbers. This is an identity function for all types. But before it's the identity function, you need to make it the identity function on a specific type. So basically, this is for all types A, an identity function. A to A. And in the first for all, you still need something that accepts that type. But the capital A does not occur in the body of the expression in the way that we're doing this. So for example, one of the things that you could do, A has to be a type. You could let's take this polymorphic identity function. And you can take that function and you can apply it to, let's say, nats, which is going to be a type that we're going to have by the end of today's lecture. Then computationally, this should reduce to, which again, I still haven't motivated, lambda a dot a, which is something of type nats to nats. So that is called the polymorphic identity function. This is how we take propositions from propositional logic and turn them into types in predicate logic. We take all of the propositional variables and we quantify over them. And then we can look at proofs of them. And in general, the proofs will have several lambdas in front of them, which strip away all of the propositional variables so that they get added to the context so that they make sense as types as you're going through. So in other words, the identity function in Racket, we typed it as A to A, but really there should be an implicit for all, except that it's implicit in the sense that we also don't have the outer lambda. Any questions about that? Then if you had logical statements like A implies B implies A, how would we translate that? In predicate logic?
For all, A is a type,
Mm-hmm.
and for all, B is a type.
Yes. Now, I'm going to introduce a shorthand notation. If we want to have nested for alls, then I'm just going to write it like this: for all A types A and for all types B. What? Then what?
A,
For all types A and for all types B, what?
A to B to A.
Yep. So it's a pretty straightforward translation. You just take all the occurring propositional variables and you slap on quantifiers that quantify those variables over all types. And one other moral way to think about it is that in propositional logic, the term lambda x dot x typed to, it's typed to A implies A, right? But it also types to B implies B. But it also typed to any arrow where the left-hand side was the same as the right-hand side, right? So not only all propositional variables, but it type checked to any arrow where the left-hand side was the right-hand side, no matter how complicated the left-hand sides and the right-hand sides were. Well, here we're formally quantifying over all types. And what are all types? Well, they're all implications, as we had before. But also, I guess this statement is more general, because not only does it give you the terms for implications, it also gives you the statement for universal quantifiers, and it also gives you the statement for type, and then combinations of those mixed into ever more complicated terms, so long as the thing in question indeed type checks the type. Now, any questions? Now, I'd like to discuss annotations. So does anyone remember the proof term that I gave that Proust fails to check? That corresponds to a valid proof tree.
Oh, you mean the last case?
This is, sorry, back in predicate logic. Back in propositional logic. Implication fragments. What was a proof term that had a valid tree that Proust could not check? Well, as an example, here's the thing. Remember that we had, for example, lambda, let's say x dot x. This had type, we could say A implies A. This is back in propositional logic, right? And then this had a proof tree. What was the proof tree in monodirectional form? What rule did I apply here?
Implication.
Implication what?
Introduction.
Yes. And then what rule did I apply here?
Variable.
Yep. And then let's say that succeeds. I'm not going to write the premises. Well, then we could also consider the following tree. We could consider what happens if we take the identity function and we apply it to the identity function. So I claim that this types to A implies A. What does the proof tree look like? What rule did we have to apply here?
Elimination.
Yes, because it's an application. So there, what we try and do is we try and take the left-hand side, and what do we try and do? Well, we don't say we synthesize its type, but anyway, what type does this have to have?
A implies A.
Well, if you look at the lambda x dot x on the right-hand side, that has type A implies A.
Something
And,
implies A implies A. Right.
So this has to be something implies something. The conclusion actually has to be A implies A, right? But what does the premises have to be? So sorry, let me explain how I'm reasoning through this. An implication, a lambda, this is implication elimination, right? So what happens is that we try and synthesize the type of the function, and then it should be an arrow, and then we type check the argument, and then the results, the right hand against the left hand side of the arrow, and then the right hand side of the arrow is the type that we eventually produce, right? So the type that we want to eventually produce is A implies A. So lambda xx should have type where the right hand side is A implies A, and then what's the left hand side?
Is A implies A?
Yes, because the identity function will type check in propositional logic again to any arrow where the left-hand side is the same as the right-hand side. And so in order to complete this rule then, okay, well, if we look at the proof of this, it's the same proof as above. So I'm going to erase the proof as above, and I'm basically going to copy it here. We add x to our context with type A implies, sorry, that should be a colon, A implies A. And then we try and type check x against A implies A, and that succeeds by the variable rule. And then here we try and type check this, or we try and type it as A implies A, right? And the justification for that is the same. We add x into our context with type A, and then x has type A because of the variable rule. This is the introduction, and this is the introduction rule, right? So that's a valid proof tree. So this proof tree shows that there exists a proof tree with this as its valid conclusion. Therefore, that thing works. But in Proust with our rules, that didn't work. Why? Because we can't type synthesize lambdas. Because here, there should be a synthesis in Proust rules. And that synthesis fails. However, my claim is that this proof tree, Proust can check this proof tree. How do I make Proust produce this proof tree? Right here. There is a Proust term which encodes this proof tree. Does anyone see what it is? I'll call this a monodirectional proof tree. So notice that in the monodirectional proof tree, we don't have any occurrences of the turn rule, right? Why don't we have any occurrences of the turn rule? Well, because that seemed to be just an artifact of the bidirectional approach when we did this. Now, the opposite of the turn rule was the annotation rule, in a sense. And in the monodirectional approach, let's say we also throw away all annotations. So how do I make this proof tree work by throwing in annotations? What was the problem? Why did this checking fail? So for example, if I switch this to checking against this, right? Then what had to happen here was that I had to synthesize this type, right? And this would fail, correct? How do I make that synthesis not fail? I can't synthesize the type of a lambda, right? But what can I do to find the type of a lambda instead of synthesis? I know there are fewer of us because of the power outage, but come on, some participation. So synthesis fails. I can't do synthesis, but what would succeed instead of synthesis?
Checking.
Right. And how do I then turn synthesis into checking?
Apply the turn rule.
That turns checking into synthesis.
Okay.
Well, how do I
No.
go the other way?
The one we just learned, annotation.
Right. So an annotation, and this fails. So fails because we would need to synthesize the type A implies A implies A implies A from the first lambda. But we can't synthesize the types of lambdas. Now we can convert synthesis to checking if we give a hint. And this hint comes in the form of an annotation. So how would I change my proof term so that in the monodirectional approach, ignoring the turn and the annotation rules, how would I get that proof tree? What would I need to do? Again, please, my approach requires a lot more participation. There are fewer people. Everyone has to participate a bit more. Just give answers. It doesn't matter if they're right. We can get to the right answer, but I need something to proceed. Or ask questions, some interaction. So what are we trying to do? Can anyone say what we're trying to do? What was problematic? What didn't work?
We cannot synthesis.
In this step, right?
Yeah.
So we'd like to turn this synthesis step into a checking step, right? So we need to provide an annotation to something. What is the something to which we need to provide an annotation, and what annotation do we provide?
For all.
No, this is just the implication. This is the implication fragment in propositional logic. There are no for alls. Annotations also existed in that language. Proust had them. The rule for annotations is, okay, I'll give you the rule for annotations. So this rule we had before. In propositional logic, we don't have to check for types. It was just gamma t. You could synthesize from that the type t if t type check to t. No more types in propositional logic. Or we didn't have them yet, rather. Okay, so what do I annotate? This was my original proof term. My original proof term is now at the top of the screen. What do I need to annotate with what?
It's like we want X to have type A implies A.
But we can't annotate variables. We can only annotate terms. And terms are either, yes, I guess we can annotate variables, but we can't annotate variables inside of the lambda. So our terms are either variables, applications, or abstractions, right? We can't annotate binding occurrences of variables. Go ahead.
Can we annotate the entire lambda?
Yes, we can. So we take this original lambda that we had, and what do we annotate it with?
We wanted to have A implies A implies A implies A.
Yep. So we give it this annotation, and then we write the second lambda. And then if we look at this term, Proust will accept as having the type A implies A. So we needed to give it a hint. The problem was that this step, we needed some extra information. That information didn't exist, but we can supply that information with an annotation. Now, if you think about the proof tree that this will produce, what it'll have is it'll have instances of both the annotation rule and also of the turn rule before, for example, applying a variable of the variable rule. And if we erase all occurrences of those from the proof tree and remove all annotations, then this proof tree recovers that monodirectional proof tree. So it's not as though this proof, speaking about it as a proof object in the monodirectional rules, is not, it's not as though this proof doesn't exist. You can't, there is a proof term that encodes that proof tree. And that proof term has this annotation. So in general, any monodirectional proof tree that you have, you can always write a proof term that encodes that proof tree, but you might have to provide some annotations to help proofs actually do the verification. Does that make sense? So annotations really help proofs along when there's ambiguity. Now, before you said you'd like to annotate X with type A implies A, right? There's actually something to that. So there's an alternative approach to what we did. Instead, we could consider what is called typed lambda calculus. And this has a different grammar. So this is a different system. And let's say this is our terms are either going to be variables or they're going to be abstractions. But now the actual variables in the abstraction are going to be annotated with types or their applications. And then types are, well, either, let's say, atomic types or arrows. So suppose that every single lambda comes with a annotation on its on the formal parameter. So every single formal parameter is annotated with a type. How would we write the identity function, for example?
Lambda x has type T.
Well,
then,
what is T in this case?
That's a denote annotation T.
But what is T? T is a meta variable for a type.
Yeah.
Let's use some, so A, B, and C are common propositional variables, right?
Yes.
So we could say, for example, lambda x A, then what?
On X?
Yes. So this is the identity function from A to A. So this identity function, and what's the type of this? In the empty context, this has type what? Well, okay, the identity function would be, sorry. The identity function would be this. But if we try and type it, go ahead.
That's A implies A?
Yes. Now, is there any other way that we could type it? Is there any other type that works here?
I don't think X works. Like it has
Well,
to be
X is a variable. Sorry, little
Yeah.
x is a term variable.
So I mean it can like B implies B, like anything, any sort of type.
Oh, so I haven't told you what the typing rules are, but B is different from A, right? And here A is already annotated at the variable at the binding occurrence level. So
So
whatever it returns, it takes something of type A and it returns something of type A because it returns X. What type does X have?
has type A.
Right. So no matter what, since X has type A, this is A implies A. This is the unique type. This is the only type that makes sense. And in general, then, if we consider, for example, the type A implies B implies A, how do you give, what is a term of that type? In typed lambda calculus. So how would I write a term of that type?
It will be lambda X, lambda Y, then
But
X.
you can't just say lambda X.
I have to say X has type A,
Yep.
then lambda Y has type B, then X.
And then if you look at this term and you try and type it, there's only one type that makes sense, right? It takes something of type A, right? And then it returns a function that takes something of type B. And what does it return? It returns X. What type does X have?
A.
Right. So in the language of typed lambda calculus, every term has a unique type. A term has at most one type. So everything is synthesis in a certain sense. You can, if a term has a type, you can synthesize its type. Now, there are certain things that do not have types. So here, consider, let's say lambda x, let's say x is something of type A implies A. And let's say that Y is something of type B. And let's say I consider the application X applied to Y. What type does this have in the empty context? So X
B.
is something of type A to A, Y is something of type B. What happens when I apply X to Y?
It's either B or an error.
Well, A and B are different, right?
Yes.
So this should not type check to anything, right?
Yeah, so it gives an error.
Yes. This has no type. So not every single term, if you think of terms as proofs, my supervisor says that every proof proves something. Well, here are proofs where they don't prove anything. They're meaningless expressions that don't. This is meaningless because you're taking some function that takes something of type A and you're giving it something of type B. And that just doesn't work. So you can say this term is meaningless. Now, but here's the thing. In untyped lambda calculus, the term lambda x, lambda y, xy could be typed. For example, to what? What's a type that this term can have?
A implies B implies A implies B.
Yes, very good. So if x is given a function of type A implies B, and then y is given something of type what?
A implies B.
A. And then the application gives you something of type B, right? So, well, why? So in other words, this corresponds to the typed term. So how would I rewrite this term with annotations on the binding occurrences of the variables? How?
X will have type A implies B. Then Y will have annotation A.
And then xy. So here's the thing. In typed lambda calculus, every single term that has a type has a unique type. Whereas in untyped lambda calculus, this could type to many things. But at the same time, not every single typed term is meaningful. Here's an example of a typed term that is meaningless, right? So that brings up the question, is every single untyped term have a type? Is it possible to put annotations such that any untyped lambda calculus term can be made a meaningful term with a unique type in typed lambda calculus? So the question is really, does every proof prove something? Where I'll put quotations around the proof. The question means, given an untyped term, given lambda calculus given given an untyped lambda calculus term, is there some t with, let's say in the empty context, t has type t, or I could even write type checks too. So what do people think about this? Is this always possible? Does every theorem prove something?
Is
Sorry.
nothing considered something?
Go ahead, sorry.
Like, is nothing considered something?
Well, terms can't be empty because terms are defined by a grammar, right? And the grammar doesn't allow for empty terms.
I would say yes.
And yeah, that's a reasonable thing to believe, right? So, well, let's try this. Does anyone have does anyone think no and have an argument for why it might be no? Or can they suggest a term that can't be typed? Go ahead.
When you say something, do you mean that it's unique in its own way, or that they all prove, even if it's all the same, they prove the same thing? Like, obviously, a lot of the proofs we've shown have shown the same solution over and over again, just in a different way.
Right. So I'm asking T in the question is an untyped term. So T doesn't have annotations. So T might be something like this term that I'm highlighting right now. And then the question is there some T? So a T, capital T that would work is this for that term, right?
Yeah.
But there are a bunch of other ones that can work. Can you think of another one that would work for that term?
A. I might be wrong.
Well, one way of going about it is just changing the names. Like A is different from C, for example.
Okay, I see.
So what then give me another type that this will type check to.
So you're saying change the name, right? So if I take a long time to read these because I'm still trying to get used to like the language of it.
Right.
So can you add a random variable like C, like you were saying?
Sure. So can you give me an example of what the type would be? Give me one answer is this one, right? What's another answer then?
Like if parentheses A to B goes to C, then doesn't that
But here's the problem. I think of, since A to B is the first factor, think of X as being a function that is A to B. And then X is the function, Y is the inputs to the function. So it was important that this A matched up with this A, right?
Oh, I see.
So try again.
Oh. Yeah, so it has to match. Okay. Well, could you do B to A?
Sure.
And then the second one would be B, so it matches.
Yes. And then what's the final output when you apply one to the other?
I imagine A.
Yeah, exactly. because this is a function that takes something b to a. This is something of type b, and then what's the actual body of the expression? It's the application, right?
Yeah.
So once you feed b into the machine that says b implies a, you get a back, right?
Yeah.
So that's another answer, and that answer is different from that answer. Now, here's another answer. You could also say a implies a, right? Implies a implies a. And then in general, they don't have to be propositional variables. They can be even bigger things, right? So can you give me an example where instead of a or b, you actually have a more complicated expression?
More complicated. Would like multiplication count as a more?
Oh, so the only things that we have for types, a type is either a propositional variable, a, b, c, etc., or it's an arrow. Type implies type.
Oh, okay. So could you do something where you have like what is it's like the law of what is it called? Like the law of transitive property, like if A is equal to if A is equal to B and then B goes to C, then goes to C. Could you write something like that as a type?
Well, we don't have equality, and it has
But
to
I'm
be
saying it's like an
something.
arrow.
Oh, okay. So you're saying, for example, A to B. Oh, I see what you mean. I see. 1 second. Oh, okay. So let's say you have something of A to B. And let's say you have something of B to C. The problem is if you wanted to conclude something of A to C, the proof term would be that you'd form a function that takes something of type A, and then it would take, let's say, that proof term would look different. So would the statement that you said is a true statement. So let me write that down. So you're saying that A implies B, and A implies C implies that A implies C, right?
Yeah.
So what's a proof term for that? This proof term that we started with originally doesn't work for it. But if you wanted to write a proof term, let's say that X is a proof of A implies B, and Y is a proof of A implies C. Then how do you get a proof of A implies C?
I mean, because it's Y, right? Because it's the output.
Oh, sorry, typo, good. I want B implies C for the second one, right? Sorry, whoops, this is what you're talking about.
Yeah. Wouldn't B be our X?
No, because the way that this proposition is read is that the implicit bracketing is this. So X becomes A implies B, and then Y becomes B implies C. Well, those are the types of the things. So the question is really, don't even think about it grammatically. Think about it if you know A implies B and you know that B implies C, how do you know that A implies C?
Because B goes to C and you can do like substitution.
How would you prove A implies C if you know A implies B and B implies C? Informally.
That's what it's like, kind of. I just think of it like substitution. Like if you know that B implies C, then you can put C as B. And then That's
But
kind
you
of the way
can't
I
go
think.
the other way around, right? It's
Oh.
not true that C implies B. How do you prove that something implies something?
I don't know. I guess I
Well,
kind of.
we had a proof rule at the very beginning of the course when we were doing informal proofs. How did you prove like an implication? There was hypothetical reasoning, right? Well, what did we do in hypothetical reasoning?
I don't recall right now. I can.
Oh, so we assumed the left-hand side and we proved the right-hand side under that assumption.
Yeah.
Does that make sense?
Yeah.
So what we're going to do in proving A implies C is we're going to assume A, right?
Mm-hmm.
And how do we write an assumption?
Don't we kind of write it like a hypothesis, like if we're assuming something for it to work?
Right. But if we look at the statement that we're currently writing, we've already assumed two things, right? We've assumed this and we've assumed this. So how do we assume A now?
Don't we just write it as like a hypothesis that we do assume A?
But now in lambda calculus.
I would imagine lambda x colon.
Oh, let's do it in the untyped world at the moment. So just choose a variable. Little a, for example, right?
Yeah.
Okay, so now little a is a proof of A. Now, how do we get a proof of C?
Well, it would be like lambda b, right? Because
Lambdas form implications. So we're working in a context where X has type A implies B, Y has type B implies C, and A has type A. How do I get something of type C?
well, the only way to get to it is b.
Yes, how do I get something of type B?
It's your y term, right? Or like it's the second term because b implies c.
Oh, well, think about it like this. Let's suppose that you have a vending machine that has walnuts in it,
Mm-hmm.
and they have a shell. And then you have a coin, and then you also have a walnut cracker. How do you get the contents of a walnut? So this is a coin.
Yeah.
This is a vending machine.
Well, you
And
would
this is a
put
cracker.
the coin in the vending machine,
Right.
and then out would come like the walnut and in the wrapper.
Yes. And then what do you do with that?
And then you open the wrapper.
Right. Now, the last thing that you do is you open the wrapper, right?
Yeah.
Now, we can think of let's say our coin is our A.
Yeah.
This vending machine, which takes the coin, is our X. And this walnut cracker, which takes the output there and produces a C, is Y, right?
Yeah.
So the last thing that we do is we use Y on something. What's the something that we use Y on?
Would it be C?
But
B.
the
It would be
only
B.
thing, it has to be in terms of X, Y, and A.
Okay. So it would be, well, you're saying it's like a coin, so A would go into X, right?
Right. And how do we write that?
A implies X.
Well,
is it
this is in the grammar of terms. So in terms, all that you have is you have variables, you have abstraction, and you also have application.
So then it would be AX, right? Next to each other.
Close. The
Or
function
XA.
say it.
XA.
Yes. So X is the function, the machine, the vending machine, and then you give it a coin. Then you get something from that. That's the walnuts. And then you take that and you feed it into the walnut cracker and you get the content of the walnut. So does that make sense?
Yeah.
So in other words, before I was asking you to produce some other type that this term has, right? And you suggested something like this transitivity of equality. Well, a term of that type looks like this, which is different from this, right?
Yeah.
So the answer that I was looking for there, where if we looked at something more complicated in place of A, you could also type it as, for example, instead of A, you could consider A implies A. And let's just replace that with what we had for A before. So if you have A implies B, and then you give it something of A implies A, and then you'd get something of type B, right?
Mm-hmm.
So this thing right here is another valid type for the original proof term that we had.
I see. Yeah.
And then in your example, you could also replace any of A, B, and C, all occurrences of them, with any more complicated type whatsoever.
Yeah.
And it would also work. Go ahead.
Yeah. I always get confused because I feel like A implies A is kind of obvious.
Well, there's a proof of it. The proof is
Yeah.
short. Lambda XX, the identity function, is a proof of A implies A.
Yeah. I just feel like it's very redundant. So I always.
Well, then you could, instead of writing A implies A, write something more complicated for this A. You could write A implies C. That would also be a valid type.
I see. Okay. Thank you.
Right. Okay, but now you understand the question. The question is, if we have any untyped term, is there some type that works for it? So for example, for the term that you produced, the answer is yes, there is some type. It's the type that we had before, this sort of transitivity type. For the term that I started with, the answer is yes again. Here is one such type. Here is a second such type. And then for any specific type, we can produce a typed lambda calculus term where we explicitly annotate the formal parameters, and then that term has a unique type if we write colons after every parameter. But the question is this always possible? So do you understand the question?
Yeah. Then I would argue yes, that every proof proves something.
So that's the thing that you did suspect, right?
Yeah.
So, okay, and now that the question is clear, can anyone think of a term that might not prove something? What's a proof that's meaningless no matter how you look at it? So I can rewrite the question. Is there a proof? That's meaningless. No matter how you look at it. And so, okay, I'll give you the term. Can you type the following term? Does lambda x applied to x have a type? Well, can you, so try and give it a type. Well, first off, it's a lambda, right? So the type should probably be an arrow type, right? So what should the left-hand side of the arrow be? Give an example.
Say A implies A.
Sure. If the left-hand side is A implies A, then on the right-hand side, we're trying to apply something to something, right? And so we're trying to apply something of type A implies A on what? Something
A?
of type A implies A.
Uh,
What we want to apply it to is something where this is the same as this, right?
yeah.
So X should be an arrow type, right? Where the left-hand side of the arrow is equal to what?
A implies A.
Yes, but A implies A was the original type of what we had for the arrow, right?
Yeah.
So for example, if we wanted to make the left-hand side be A implies A, then what we'd say is, oh, well, it should be A implies A implies A implies A. That should be the left-hand side of the arrow. But then the left-hand side of the arrow should be the entire thing. So whatever it is, it should be an arrow where its left-hand side is equal to the entire thing. So perhaps the type that we'd like to write is that it's A implies A implies A implies infinite descent. Because then if we take that type, then A implies that is the same as the original thing. But we don't have infinite types, so that doesn't work. Now you could make this argument formal, but you can, do you see sort of now where we run into the problem?
Yeah. So we will get a contradiction for finite number of implications.
Right. So
with that, so this is like a counterexample to
yes,
to the thing that we are trying to get.
so this term does not have a type. In our language, we'll actually see later that using for alls, it's possible to give it a type, but under a very restricted hypothesis. Well, let's look at this term actually. Let's look at this term, lambda x, xx. And let's do a computation on it. Let's take this term and let's apply it to the term lambda x, xx. So what does that equal to in computation? Or I'll write it as reduces to. So this is reduces to. So this is now computation. Before, when we were discussing substitution, how did applying something to a lambda work?
Wait, I guess it reduced to itself.
Oh, well, let's do it step by step. So what do we write here? I'll remind everyone that the rule for computation is that if you take a lambda expression and you apply it to, let's say, S, then this reduces to, in one step, T with X substituted with S, right? So what does this reduce to? Just following that rule. Well,
X X substituting.
we take the body and we substitute X with what?
Lambda X and XX.
Right. Now, in an application, how does substitution work? In an application, to do substitution, we just substitute in both factors of the body. I will not write the entire thing. And then after we do this, X, we're substituting into a variable. The two variables agree, so what do we get?
Lambda X XX and another parenthesis,
Yep.
lambda X XX.
So we get the term itself. And then if we look at how this missing a parenthesis, this computation happens in the next computational step, it reduces to itself again. And this never stops. So this is a non-terminating computation in lambda calculus. Now, the next thing that I'm going to say is absolutely mind-blowing, and it's actually true, and this should melt your brains. What's the most surprising thing that I could possibly say? About this. That's a true logical statement about lambda terms and computation. So this is the most surprising thing possible. Every computation with typable terms terminates. In other words, the fact that this computation never stops is related to the fact that the term lambda x, x applied to x is not typable. And this is called the normalization property. or just normalization. Normalization of typed lambda calculus. So it is impossible to write a computation which is non-terminating if you have well-typed terms. In other words, another proof, the following, if we assume this results, then the fact that this computation doesn't terminate proves that the entire expression with that application is not typable, which is different from saying that each one of those is not typable, as we'll actually be able to see later. Because in using for alls, we will be able to give each one of those a types, but the application will not have a type. So in other words, having types is a very strong property. It is incredibly surprising that you can avoid non-terminating computations by using typed terms. And this is a very difficult result to prove. Has anyone very surprised by this? With all three people in the meeting? Okay, this is a very bad situation of power outages.
A quick question.
Yep.
Does the converse statement hold true?
No, because you can write, so it's possible to have features like if. You can write, for example, if true, then like 0, and then you can write non-terminating computation.
Okay. So if a computation does not terminate, it will not be typable.
Yes, but the
So-
converse isn't true. You can simulate if using lambdas, and then you can write a computation that will avoid doing this non-terminating thing.
I see. So it's a way to check whether a computation is typable.
It's a way to check that a computation will be terminating.
Yes.
So in general, the idea behind types, the main idea in programming languages worlds, why do people care about types? Types guarantee the absence of certain errors. So type programs that do not have type errors, that type check, are provably well behaved in certain ways. So for example, in most programming languages, you could write a function like, let's say, define maybe add 1x. And then you'd write, you can give it a definition as its output is x plus 1, right? If you wanted to define it. Now, this function will throw a type error unless x is a number. So in Racket, we could write an informal contract saying that this has type number to number. But in fact, Racket does have a way of enforcing contracts. And in other programming languages, like most conventional imperative programming languages, C, you'd actually write add 1 takes an integer parameter x, for example, and then returns an integer. And if you try to call the function on something that wasn't an integer, it wouldn't even compile the program. It would get rejected by the type checker. And so having programs pass the type checker ensures that you won't have mistakes like adding something to something that isn't a number. But in a much more powerful and much more surprising way, having programs type check in lambda calculus also guarantees that every single computation terminates. And that's incredibly surprising. Is a very surprising such property. Now, okay, so let's take a 5-minute break now, and then we're going to get back to proof assistance. So let's resume at 4:02. And okay, this power outage situation sucks. I'm probably going to move some of this until I'm going to maybe hold a makeup class with when people actually exist and have power out. I guess I can't ask any of you in the meeting right now as to when they said they would put your power back on, because by definition, you're the people who are not in the power outage situation. Okay, anyway, see you at 4:02. Okay. Welcome back, everyone, all three of you. Any questions? So in summary, what we've done so far, and this has been going much slower than I expected because of the Faro situation, we briefly discussed what the rules were for what is our analog of the implication fragments in predicate logic. We had all of these rules. For types now, well, types and terms are mixed, but the things that look like types are now their implications for all statements or just this constant construct type. Variable rules stays as before. The implication, introduction, and elimination rules become these more powerful and beefier for all introduction and elimination rules. We have annotations, and we have the turn rule. And then I suggested, like, what's this idea behind annotations? We had it before. We had annotations in Proust's grammar. For example, when we asked Proust to check a term before, what we were doing is we were trying to synthesize an annotation. That's how it's implemented. And then it would go to type checking mode. But really, the idea behind an annotation is that if terms were fully annotated, in other words, if they were typed, if all lambdas had types, and if all, for example, or introduction statements had already types supplied as a way to interpret them, then we could make a grammar in which we could proceed using only synthesis. Only synthesis would suffice because all of the annotations would already be there. And that's the idea behind type lambda calculus where you have annotations. But even if we're not using that, we can still make every single regular monodirectional proof tree be a bidirectional proof tree if we just supply explicit annotations at every place where we can do them. And we can do that with annotations. Such as the tree that I showed before, the term that Proust could not check. It can be made to check if you put an explicit annotation on that lambda. And then here I said, well, okay, so that discussion was something back in propositional logic. Going back to predicate logic for a second, or forward, the types of things that we have in propositional logic, A implies A, or A implies B implies A, the way that we made them into statements in predicate logic was to actually explain that when we used A and B, we meant propositional variables. We meant that they ranged over all types. And so we put a bunch of quantifiers in front of the statements, and that converted statements in propositional logic to statements in predicate logic. So for example, A implies A now became this for all A in type. So for all possible logical statements that you could write, for example, although it's not only logical statements, A implies A. And a proof term for that was what is called the polymorphic identity function. Lambda capital A, lambda A. And if we were working in typed lambda calculus, you could actually think of that takes a type and then returns the type lambda term. What typed lambda term would it return if we were, if we wrote this as a term in typed lambda calculus where every single lambda has to have an annotation, then what would it be? So I need to put an annotation on the A, right? What would I write?
A has to be type.
Yep. And then what's the body?
Then lambda little a has to have A, type A.
Yes.
Then A.
Yes. So in this term, it looked like A did not occur in the body of capital A did not occur in the body of that lambda. But if we were working in the typed setting, then the capital A actually does occur. Sorry, in the typed lambda calculus setting, then it actually does occur, because if you feed it A, it produces a specialized proof term where there is actually substitution that occurs in the annotation of the formal parameter. So in typed lambda calculus, that's capital A is not superfluous from a computational sense. Although you can say that the type annotations on their own are necessarily computationally superfluous. If you just care about how this behaves on subsequent terms, then, and you don't care about throwing typing errors, then this A does not participate computationally. But if you actually care about producing a term with a type annotation, then it would participate computationally. But anyway, so with typed terms, we can always try synthesis, but that synthesis might fail. You can write terms which are meaningless. And then we got to the question of, well, can every untyped term be made meaningful? Can we always provide annotations so that type synthesis succeeds? And the answer was no. And we found one such term. And we noticed that if we applied this term to itself, we got a non-terminating computation. And then the surprising result is that, well, this is only because there were non-typable terms involved. Every single typable lambda term, it represents something which is a terminating computation. Right. So now going back to this, let's consider we have the grammar that we had before. Now we're back to predicate logic. And consider the following term. In the empty context, right. So let's suppose that I make global definition. I'll define ID to mean for all A in type, A implies A. And I'll run this global definition. Oh, okay. Sorry. I'll define this as ID type. And then I'll define ID to mean, so I'll write the term lambda. Okay. This is the polymorphic identity function. And I'll check my definition. Check ID against ID type. So in other words, by ID, I really mean the following annotated term. In other words, remember before when we, for example, had the identity function applied to something, and when we were trying to do the for all elimination rule, we could not synthesize its type. By ID type, I will mean something that's essentially an annotation. So this is something where I could synthesize the type. So for example, in the empty context, ID synthesizes to ID type. Because it's an annotation. Now, suppose that we somehow have a way to make definitions work so that ID indeed synthesizes to ID type. Then consider the following thing. Does the assumption make sense? I'm just supposing that ID type means this type, and ID means this annotated term, so that I somehow have names and definition lookup, and it's possible for ID to synthesize type ID type. But in this case, let's consider the following expression. In the empty context, I'm going to consider, let's say, ID, and I'll apply it to ID type. And then I'll take this and I'll apply it to the identity function. And I claim that this, from this, I can synthesize the type ID type. How would that work? What rule would I have to apply here?
Elimination.
Right. Now, as its hypothesis, I'll have to try and synthesize ID type, ID applied to ID type. So really, I would have to synthesize its type here. And how would I synthesize that type? What rule do I apply again?
The turn rule?
Well, it's an application, and applications are, we can always synthesize, right?
Yes, that will be elimination again.
Yep. And now the hypothesis that I told you is that ID is something that synthesizes to ID type. Now, ID type is the same as what I had before. The problem is that, look at this. In order for this rule to work, our implication elimination rule is that if we have some application, F applied to A, then under the hypothesis that from F we can synthesize a for all type. And under the hypothesis that A type checks to T, we can synthesize, synthesize type W X substituted with A. right? So here ID type does not look like a for all statement, but I also said that ID type, by ID type, I really meant for all X in type, or for all A in type. A implies A. And then if I'm able to synthesize that type, what do I have to check?
ID type check to type.
Yes, good. And this will succeed because we look at what the ID type was, and it was a well-formed type. So this will succeed. And both of these, this will happen and then in some number of steps. And then what's the conclusion? So if both of these succeed, then what do I get from the synthesis?
A to A.
But what is A?
Type. Wait, is it type?
No, because A was quantified over type. A was the variable of quantification. What was the parameter that was passed?
It's ID.
Yes. So what do I synthesize?
ID implies ID. With
ID type.
each occurrence,
Not ID. ID
relevant
type.
occurrence of X replaced with ID type.
Well, we take A, right, and we substitute A with ID type. So like this is what you were saying, right?
Yeah.
Okay, well, we're trying to synthesize this application, right? So now what's the next thing that we have to check? So in this implication elimination, what else do we have to check? So this is an application at the top level, right here. And we were trying to synthesize its type. And we synthesized the type of the first argument, right? As ID type to ID type. Now, what do we have to check?
Whether ID type checks to ID type.
Why did you say whether ID type?
Is this, wait a second. No, it's ID.
Good.
ID type checks. Right?
To ID type. And this will succeed because if we look at what ID is, well, it's this annotated term, but this annotated term you'll type check it against ID type, it'll go into synthesis, and then it'll go back into type checking, and then type checking will succeed. So in other words, the type of ID applied to ID type applied to ID, this has the same type as ID. Well, this synthesizes type ID type in the empty context. So this synthesis succeeds. So we are going to need a definition, a notion of definition lookup. That's one thing. That's one of the things that we're going to want to add to our language in order to let us build up terms. Because if we try to write this proof tree with ID and ID type replaced by big expressions, especially if we replace ID with an annotation where we had ID type, then this would be very messy. So one of our actual proof assistant wish lists is a way to make definitions. Now, what happens if I look at, for example, ID and I apply it to type? Here, let's do this example in bigger space. So I'll take the polymorphic identity function. I'll apply it to type. And then I'll apply this to ID type. And I'll try and synthesize the type of this. What do I get? What rule do I apply?
For all elimination.
Then what do I try?
Try to synthesize ID applied on type.
Let's try that.
That's for all X.
Well, so then what do we do? What rule do we apply here?
Okay, it's another for all elimination.
So then I try and type synthesize ID, and what does ID synthesize to when written as a for all statement?
It's for all X that has type T.
What is T?
T is a type. Then
Actually, technically we had A before. Let's keep it as an A.
okay.
So what do we synthesize? For all A in type what?
ID type. Is that right? No.
Well, what is the type? Well, so it synthesizes ID type is one answer. But what is ID type? We can rewrite ID type as a for all statement.
Oh, it's A to A.
Yes. So that's what ID type is. If we expand the definition of what ID type is, it expands to this. And so if I'm able to synthesize that, then in order to complete this, what's the next thing that I try and do?
Type check type. See whether type has whether type is a type.
Yes. You try and type as type, and you can type as type. And so what's the result of this synthesis?
A implies A.
But what is A?
A is ID type.
Nope.
No, type.
Yes. So what do I get?
That's type implies type.
Mm-hmm.
With all occurrence of A substituted with type.
Yes. So you've done that already. type is just this construct. It doesn't have any internal structure. It's just capital type. Okay, and then what's the next thing that we do?
Type checks ID type
Mm-hmm.
as type.
Yep. And that succeeds. ID type is a type. So what's the result of the overall synthesis?
The overall will be type.
Yes. So in other words, if we take ID and we apply it to type, and we apply that to ID type, then our current version of Proust with the rules that we had before, this makes sense as type. So in other words, this expression right here is a type. This application is a well-formed type. Before, if we looked at the rules that we had, there were 6 variants, and we said that like abstractions are definitely not types. Applications, you'd like to say that they're not types as well, but here's an example of an application that defines a well-defined type. Now, what does this mean? Well, if you took ID and ID type and you just replaced those things with ID type as being this, and with ID as being this, but with ID type replaced with what it is, then you wouldn't need definitions. Then you just have a fully expanded term of where an application typed as a type. So this application should be a type. In other words, it should classify terms. But what terms does it classify? What rules allow us to classify terms as being members of a type that's at the top level in application? How do we determine whether a term has this type? And this makes sense as a type with the current rules that we have. So if we accepted the current, there were 9 rules. If we accepted those 9 rules, then we have to agree that this defines a type. But what are its terms? What does this type really mean? What do you think this type should mean? So first off, what is ID applied to type? First off, what was ID? ID means what?
Lambda A, capital A, and lambda small, a little a.
Right. So, and this is the polymorphic identity function. So when we take ID and we apply it to type, what we get is what? Computationally.
On type to type.
That's its type. Oh,
Oh.
sorry. This is computation arrow. Okay, I'll write an equality. Let's write under computation. Let's write actually triple arrow. Computation. So under one step of computation, what does that become?
Lambda type.
But type isn't a formal parameter of a lambda.
Lambda A. A.
Yes.
Oh.
So this in untyped lambda calculus doesn't appear. So it's just the identity function. But really, this should be understood as having type to type. So this is the identity function on types. And so if we apply the identity function on types to a certain type, what should that mean? What should this mean?
I can guess.
Go ahead.
Reduction.
What do you mean by reduction? Well,
like sort of a simplification.
okay, but what does it reduce to?
Reduced to type. No.
So if you apply the identity function to ID type, what do you get?
I get ID type.
Yes. So in other words, we said that our current rules say that this thing right here should be a type. What is the meaning of that type? Well, if we apply computation to it, then its computation suggests that the meaning of that type is just ID type. Because we've taken the polymorphic identity function, we've specialized it to be the identity function on types, and then we applied it to a type. And so we should get the original type back. So in other words, this should mean the same as type. These should be the same type. So in other words, when considering types, we are before in the Turner, well, I started writing this 3-directional arrow. So we before first started with this means equality. It means we just check for equality. Then last class we said, well, this should also mean alpha equivalence. Well, right now we're saying not only should it mean alpha equivalence, it should also mean computation on types. So for example, you can have an identity function on types and you can apply it to a type, and that should mean the same thing as the original type. You can also write functions like, for example, here's another example. Let's say you take lambda, let's say x lambda a to a, and you apply this to type. What does that reduce to?
type to type.
Yep. So in general, for lambda terms, we could have their bodies be something that looks like an arrow or something that looks like a universal quantification. And then if we apply that to type, this should make sense as a type. And it should make sense as the type to type. Now let's see whether our rules make sense of that. So first off, if we had an application, then that's bad because we can't synthesize the type of an application, right? But we can provide an explicit annotation. So let's give this an explicit annotation as type to type. Which we would do by making a global definition in practice. And so that closes that closes that binder. And let's say we apply this to type. And we try and synthesize this type. So what happens in our rules?
For all elimination?
Yep. And so we try and synthesize the type of this annotation. Let's write it explicitly. So we try and synthesize that type. What rule happens now?
Introduction for
Not exactly, because for all introduction uses implication. Sorry, it uses checking mode.
Okay, let me see. Annotation.
Yep. So annotation changes the synthesis problem into what?
Check.
Yeah.
What are we checking? Against what? Checking it against what?
Type implies type.
Yep. And now what rule applies?
For all introduction.
Yep. So this really is the same as, we should write it here. Up to alpha equivalence, we can maybe write for all A in type. Type implies type. So that's to alpha equivalence, these are the same. A doesn't occur in the body here, so these are alpha equivalents. If we rewrite it like this, then well, what does the rules for all introduction rule say?
Type has to be a type.
Yes, so we check still in the empty context whether type checks to type. Technically, we'll apply the turn rule and then we'll synthesize, but that succeeds. And then what?
Given A in type, type implies type is a type. Type checks
implies type. A implies A.
A implies A. Type checks
A. Type
is
checks
a
a type. And then that'll also succeed, right? It'll be a few more steps, but that will succeed. So if that succeeds, then this checking succeeds, then this synthesis gives me what? The very bottom synthesis. Here.
It's just type to type.
Yeah. Now, what's the next step? Now I need to do some checking for this for all elimination.
Type checks to type implies type. Type checks to.
Oh, well, if we actually look at it, if we look at what the rule is, we synthesize a type, we have to match it against a for all. So we can say that this is also for all, let's say A in type. Type. Oh, yeah, okay, then we made a mistake. We want to supply. No, this is good. For all A in type, right? This is what this type is alpha equivalence to. And then I made a mistake. This is actually alpha equivalence to just for all A type. There isn't this second type. And what we're checking is A against A type, right? But what do? We look at the T, right, in the rule. The T is this. So we type, what do we type check type against?
Type.
Yes. And this succeeds as well. So what's the result of the synthesis? The bottom one?
That'll be type.
Well, let's actually look at what happens.
Yeah. It's wait. It's
Wait a second. Let me just check this as well. Oh, right. No, right. It would be type. Exactly. Because if we're just typing it. Because this isn't computation. This is this. If we actually look at what the computation is, on the other hand, so that's a type. But if we look at the computation, then what does that computationally equivalence to? So that's computationally equivalence to type implies type. And that is indeed a type, as the calculation above shows. Now, so here's the thing. So I'm definitely going to do an extra lecture, but this is the last thing that I'll say for today. When we had, for example, the rule, let's look at, for example, what was the rule for implication elimination? Sorry, for all elimination.
that should be synthesized to W. Oh wait, do it sequentially, right? Okay.
Right.
So we check whether F can be synthesized to a for all statement.
Yes.
That is for all X in T. A for all. Yeah. That implies W.
Mhm.
Then we type checks in context gamma.
Yep.
A type checks to capital T.
Good.
And that
And then
should,
what's the result?
then f of A should synthesize to W with relevant occurrences of X
Yes.
substituted with A.
Good. Now, so here's the point. Here, if we look at the computational implementation, F synthesizes some type, right? And then in the computation, we should match against a for all statement, right? But what happens if F synthesizes not, let's say, a for all statement, but the identity function applied to the for all statement? Let's apply to that the polymorphic identity function, so ID type. Then that match will not succeed, because at the top level, that is not a universal type. That's an application, right? But the thing is that we'd like to say that this is equivalence to for all X and T, W, because they're computationally related. So for example, here, after we synthesize the type, we try and match it to a type of this form. But what happens if it can only be matched after one step of computation? So the idea is that whenever we, for example, try and synthesize a type and try and match it against something, we should allow computation to happen in types. If we, before trying to match its form, we should reduce it. We should let this computation occur. And then if after the computation, it's a for all type, then we proceed. Similarly, in the rule for checking, if we're trying to type check a lambda, let's say lambda xt, if we're trying to type check this against some type. So here's the rule for what happens if it's a for all statement, right? So, oh, and we have to make these alpha equivalent, right? So we have to make these two x's match up. Then what are the hypotheses of this rule?
T has to type checks to be a type.
And
in context gamma and for all, I mean not for all, X in T.
Yep.
P has to type checks to W.
To W, good. Now notice the two things that happened. Well, first, in order for this rule to apply, both of these had to match up. Also, in order for this rule to apply, this had to be a for all statement, right? So what happens if it's not a for all statement? What happens if it's an application? Well, number one. And number two, what happens if the variables don't match up?
We allow it to compute. Right?
Yes, and then we rename variables. So in general, here when we're trying to synthesize and match against the type, or here when we're trying to match against the type in inference, in both cases, we should allow computation and renaming. So this is the first place where computation comes in. The general idea is that if our grammar allows these things, then our grammar allows us to interpret ID of the polymorphic identity function specialized at type apply to ID type to synthesize type. So that's a type. So what terms does it classify? Well, the rules say nothing about what, they never let you infer an application type, unless maybe by the variable rule, unless we added a variable to this to our context. But otherwise, by one computational step, it's something meaningful. So we should consider types equivalent if they're computationally related. And so here and here, it looks like we perform computation. Now, the other thing is that computation might be very poorly behaved. Computation might cause divergent computations, ones that never terminates. So the other thing that we're going to do is we are going to write our proof assistance so that whenever a computation is performed, prior to performing that, we ensure that the thing that we're about to run a computation on is well formed. So in the case of types, it would be checking that the type checks to type. So for example, now the hypothesis and the synthesis rule might look redundant because the first thing that we're going to do is we're going to want to run computation on this. But if we're going to want to run computation on this, then we're going to first have to type check whether the entire thing type checks to a type. Then we're going to run computation on it. Then we're going to see whether whatever the result is, and it's going to terminate because the first thing we do is that we check it's well formed before starting a computation. Then the computation is guaranteed to terminate in finitely many steps, and then we can try and pattern match against the two of them. So that's how computation comes into the proof assistance, and it comes into the proof assistance even more when it comes to equality types, which I was hoping to discuss today, but I didn't get to. This is very tricky. Any questions? So in general, whenever we have any type checking or type synthesis statement and we're looking at an implementation of it, if the actual type has a specific form, we're going to have to run computation before we can determine whether indeed the type has that form. And in finitely many steps of computation, it's going to get down to some final form. And then we can ask, is that final form correct?
Before we do computation, we have to verify that it is indeed a type.
Yes.
To ensure that the computation stops.
Yes. So in our implementation, I'm not exactly writing it in the rules. The rules don't have that statement in it. The rules will not have computation in them. But in the proof assistance, the implementation will be such that you will only run computation on well-formed terms. So in the case of types, that will mean that the types will type check to type. This will actually guarantee that our proof assistant will never run forever. If you look at the current version of Proust in Prabhakar's handout pages, some of those checks are missing. So right now it's possible to, for example, type check something. Right now, if you go to Prabhakar's code and you type in, let's say, so there's this check one function, which basically synthesizes, it parses the term and then it tries and synthesizes type. So you can write something like check one. Then let's write something like type has type. Then you can write this divergent combinator, lambda x applied to x. And then you can apply it to lambda x applied to x. And right now, that will diverge, but it doesn't have to with a very small modification. Actually, I'm not even sure if this modification is already in there. Also, I think what I'm looking at is the answer to a subsequent, no, it isn't the answer to a subsequent homework problem. This is the correct one. Let's see if I've already added the rule in. Okay, I can share this. So you should see Racket now. Let me just look at the annotation case. Oh, well, that's strong reduction. What about for type synthesis? Okay, so I've added this check in. I'm going to remove this check, and I'm also going to remove in type checking. That the check doesn't exist there. So here's this version of the code. And I'm going to ask it to check one. Well, check one is really the same as, well, actually, no. So for the predicate version, this will be the function for checking proofs. And I'm going to claim that type has type divergent combinator. Now, notice how this term always reduces to itself. So the computation won't actually cause memory to run out because it's well behaved. Whoops. And now the computation is sitting there. It's not running out of memory because the term always reduces to itself. So it'll just keep on running forever. The memory isn't going up, it's just staying still. And the line, there are multiple lines that prevents that you can insert. But here's an example of where you are allowed to run computation without checking it. So in this case, what would happen is that the turn rule would be applied. You'd be able to synthesize the type as type, and then you try to see whether type is equivalent to the divergent combinator. And then in order to see whether those two types are equivalent, it'll take the divergent combinator and it'll try and put it into a normal form. In other words, it'll try and reduce it to something so that the comparison can be made. And it never reduces to a final form. It always reduces back to itself. So for example, you'll see that in the definition, when we actually get all of these rules in play, so there will be computation, and computation will be, in the most general way, this strong reduce rule. This is an implementation of computation. So this is with Booleans and equality. This is with equality and Booleans, all of the rules inside it. Then if you look at, for example, type checking, in the last case, type checking has a rule for turn rule. So how does turn rule work? You try and synthesize the type, and then you see whether that is equivalent to the provided type checking. Now, what's the implementation of equivalence? Well, it tries to bring both of them to a normal form and then tries to compare them with alpha equivalence. And this computation then diverges. So I'll explain this tomorrow, and perhaps also in another session, because if people still don't have power, I'd like to actually have some people in this class. But this is the first answer to the question of how does computation enter proof assistance? And probably the most surprising thing that you learned today is this statement about normalization, that being well-formed actually prevents divergent computations. That is an incredibly surprising statement for me. Well, have a nice day.
You too.
Bye.